5.5, linearization and differentials. So the good news is these really aren't hard. So it'll be kind of a nice little change of pace as far as like difficulty level. It's just like the first derivative. They're pretty easy, like pretty chill. So we have, I know you have this in your notes, but the linearization of x is f of a plus f prime of a times x minus a. And so that's the formula we'll be using for these first few problems here. They say to find the linearization L of x of f of x at x equals a. And then how accurate is the approximation L of a plus 0.1 approximately equal to f of a plus 0.1. Find the comparisons following the example, or following example 1. Anyways, so number 2, we have f of x is equal to the square root of x squared plus 9, and they tell us that a is equal to -4. So the first thing I'm going to do is I like to go ahead and try to find some of these things that I'm going to need as far as like the problem goes. So like I know I'm going to need f of a, so I'm going to go ahead and evaluate that first. So f of a, or f of -4, is the square root of 16 plus 9, or the square root of 25, which is 5. So that's going to be the first part of my linearization. So I'm just finding things step by step. Next thing I'm going to do is I'm going to go ahead and find just the derivative of f. So f prime of x would be, I'm going to think about this as if it is x squared plus 9 raised to the 1/2. Just to simplify it, make it a little easier to think about. So that would be 1/2 times x squared plus 9 raised to the -1/2. And then the derivative of the inside is just 2x. And so then simplified of that is going to be 2's are going to cancel. And then this stuff is going to move to a radical on the bottom. And so I'm going to end up with x over the square root of x squared plus 9. So I only really need this as far as setting it up. So now I'm going to take and I'm going to evaluate this at a. So f prime of -4 is -4 over the square root of 16 plus 9. So again, that's just 5 on the bottom, so -4 over 5. So now I can use this to write my linearizations. That's just all the setup. So officially part A would be L of x is equal to f of a, that's 5, plus f prime of a is -4/5, so -4/5 times x minus a is -4, so that's actually going to be a +4. And then I'm just going to distribute this through. So I've got 5 minus 4/5 x minus 16 over 5. And then just to get a common denominator to simplify this all the way down, 5 would be 25 over 5. So I've got L of x is equal to -4/5 x plus 9 over 5. So that's my linearization. So now I need to see for part B, I'm going to try to write this out, what I'm supposed to be finding here. If L of a plus 0.1 is approximately equal to f of a plus 0.1. So essentially I'm taking my -4 and I'm adding 0.1 to it, and I'm plugging it in for L of x, and then also in for f of x to see what happens. So if I plug it in, L of negative 4 plus 0.1 would give me negative 4/5 times negative 3.9 plus 9/5. And with your calculator, that would be 4.92. I think that is an exact decimal, but let me confirm. Yeah, so this is an exact decimal. And then for f of negative 4 plus 0.1, that is going to be my original equation, the square root of negative 3.9 squared plus 9. Is 4.92037. Yeah. So you have to go a few more decimal places with these than like where you normally would, because part of the question that's asking you is essentially how accurate is it. So to find that, we take the absolute value, and we do that because we can't have like a negative value. But I'm going to essentially do the f minus the L one. So 4.92037 minus 4.92. And so when I do that, I get approximately 3.7 times 10 to the negative 4. And so my approximation is right up to this point, basically. And so what we would say is it has an error less than 10 to the negative 3. So we take 1 away from whatever this is and say that that's what our error is. So basically that's how many decimal places I'm accurate to. Because I can see, obviously, technically there's a, imaginary 0 here. So I'm to 3 decimal places, I'm exactly the same. It's not till the 4th decimal place that I'm different. So that's all that's really telling us.
So if it was if the f of negative 4 plus 0.1 was like 4.921, it would be error less than 10 to the negative 2?
Yeah. This just is what finds it for you, and I could do it. You don't have to do f minus L. You could do L minus f, because sometimes your L might be the bigger number and your F might be the smaller number. So that's why we put it in absolute value, is this number has to be positive when it comes out. And so the absolute value just allows us to do that. It's kind of like the formula for finding error in like science, like when you do labs and stuff and you had to figure out like what your error was, your percent error. You don't remember doing that? Oh, okay. Well, in fairness, y'all may or may not have actually done that last year. You took chemistry last year, right?
Oh yeah, we definitely did not do that last year.
Yeah, then never mind.
Yeah.
Well, you find error essentially by doing your actual minus your predicted, but it's like the absolute value, and yeah, anyways. Okay. It's a whole thing, but you just stick it in the absolute value so you get the positive number. So yeah, so now that problem is done. Number 4. So these are long, but I don't really think they're complicated, other than like some of the numbers are a little weird. But as long as you have, if you have your calculator, not too bad. So we've got f of x is equal to the ln of x plus 1, and a is equal to 0. So First thing I'm going to do is evaluate it at A. So f of 0 is the ln of 1. Do you remember what the ln of 1 is equal to?
E? No.
E to what power equals 1?
0?
0. So it's equal to 0.
Oh, that makes sense.
Yeah. The log base whatever of 1 is always 0. All right, so then I need to find the derivative of ln of x plus 1. Do you remember how to do that? It's a while ago.
It's just like 1 over x is ln, so it'd just be 1 over 1.
Well, when I evaluate it maybe, but not yet. Just the derivative of this. So the derivative of the ln of x is 1 over x.
So yeah, 1 over x, and then
Plus 1. Whatever's inside of here is what is the denominator of that. Technically speaking, this is a chain rule since it's not just an x, but the chain rule isn't doing anything because the chain rule just gives me times 1, so I don't have to worry about that. So that's the derivative. Now, what you were saying would be right. I don't know if that's what you were trying to do or if you just got confused, but the derivative at 0 would just be 1 because that would be 1 over 0 plus 1. So this linearization actually will be much faster because zeros and ones. So for part A, L of x is equal to f of a, so that's 0, so I'm not even going to write that. And then plus f prime of a, so that's 1, times x minus a, well that's just x minus 0. So essentially my linearization is just equal to x. Which means this is really easy because then when they want me to add 0.1 to 0, L of 0.1 is just 0.1. Now, f of 0.1, though, is going to be the ln of 1.1. And you're going to have a calculator to find that. Ln of 1.1 is 0.0953. We're just going to say that. So then now I'll do my error thing. So the absolute value of, I'm going to do L of x minus f of x on this one just because it's going to give me the positive number. Not that it matters, but as far as typing it in, then I don't have to deal with that. So 0.1 minus 0.0953 is 0.0047. So that would technically be the same as 4.7 times 10 to the negative 3. So that means my error is less than 10 to the negative 2. So obviously this one, while it looks like obviously their decimals are different, like if you rounded the numbers, they're going to basically be the same thing. So that's why you kind of have to plug it into here to make sure that like it's, you know, actually different, but okay. What's next? Oh, okay. These ones are just weird, so let me write out kind of what the instructions are. Use the linear approximation 1 plus x to the k, which is approximately equal to 1 plus kx, to find the approximate approximation. Hold on. What? To find the I'm going to write this word out because the approximation for f of x for values of x near 0. Okay. So these are a little bit weird because of the way that they present the problems. This is not something I would stress too much over, but I just want you to kind of see how they work a little bit. So the first one, there's 3 different ones within this one problem. So f of x is equal to, in parentheses, 4 plus 3x to the 1/3. So essentially, I need to first make this look like this 1 plus x to the k. And so to do that, I'm going to need to take something out of here because I can see right away that there is no, like this isn't a 1, this is a 4. So I'm going to rewrite this as, in a bracket, 4 times 1 plus 3/4 x, and then that whole thing is raised to the 1/3. And essentially, I'm manipulating this to make it look like it's supposed to end up looking. It's weird. So, and even then, the answers kind of end up being a little odd. So that's why I say don't stress over these too much. So this 1/3 can go on both of these pieces. So I'll have 4 to the 1/3, and then I'll have 1 plus 3/4 x to the 1/3. Now, I'm ignoring this 4 to the 1/3 right now. Essentially, at the moment, I have 1 plus 3/4 x to the 1/3. So this is basically this right here. So what I'm going to do is I'm going to take this exponent and put it in front of my x with the 3/4 still there. So this is going to be 4 to the 1/3 times 1 plus 1/3 times 3/4 x. And then we're going to cancel the 3's out, and so I end up with 4 to the 1/3 times 1 plus 1/4 x. And that's the answer. Okay. They're very odd, like low-key kind of pointless. I feel like I would not be worried about this like showing up on the exam. Really, I haven't ever seen a question like this in any of the questions that I've looked at. Not that I've looked at every single question ever, but like I've looked at a lot. I'll look at B, but we probably won't even do C because just it's not that big of a deal. But so B is f of x is equal to the square root of 2 plus x squared. So I need to rewrite this one to try to get it essentially in the form of the previous one, but where I have it raised to a power. So this is going to be the same as 2 plus x squared to the 1/2. So I'm going to take out a 2. So So I've got 2 times 1 plus 1/2 x squared, all raised to the 1/2. I can raise each piece to the 1/2 because I know ultimately I'm not doing anything with the 2 out front. I'm going to go ahead and just write that as the square root of 2. So I'll have the square root of 2 times 1 plus, I'm going to write this as x squared over 2, raised to the 1/2. Put that 1/2 in front of that there. I'm just going to draw that. So then this is the square root of 2 times 1 plus x squared over 4. And that's all you have to do on those ones. Let me look and see something important. I don't know. You feel okay with those?
Yeah.
All right. I'm just going to skip C then because it's not that big of a thing. What is next? I feel like that should not be the last. Okay, I was like, there's no way that's the last question. 12. These ones say approximate the root by using a linearization centered at an appropriate nearby number. So I have the cube root of 26 is the problem. And it wants me to evaluate this by using a number that's like close to it that I essentially know the cube root of. So what number near 26 do you know the cube root of?
27.
Yep. So essentially, I'm going to look at 27 as far as that goes. So basically, I'm going to say x is equal to 27 as far as like my linearization goes. Because basically, I'm going to do a modified version of what I was doing in those first couple of problems without actually doing the error part. So I've got f of x is equal to the cube root of x, just generically, or x to the 1/3 if I want to write it that way instead. F prime of x would be 1/3 x to the negative 2/3. And my x is 27. So f prime of 27 is 1/3 times 27 to the negative 2/3, which is basically 1/3 times 27 to the 2/3, if I just move that down. So 27, cube root of 27 is 3, 3 squared is 9, times 3 is 27, so this actually just ends up being 1/27. They don't always work out that nicely, but they do a lot of times actually. And so I have that value. I did not find f of a yet though. And essentially it's like hard because it says like x is equal to 27. That's basically my a value. So I need to do that as well. So f of 27 is equal to the cube root of 27, which is 3. And so anyways, essentially that's what I'm dealing with. So the cube root of 26 should be approximately equal to the linearization for 26, which would be f of a, 3, plus f prime of a, 1/27, times x minus a. But in this situation, x is the original number that I was given. So 26 minus 27. So basically all this does is make this negative. So I've got 3 minus 1/27. And when I do that, 3 minus, what? I get 2.96. So basically the cube root of 26 should be approximately 2.96. Now, if we're so inclined, I could actually find what it is. And it's not until the 4th decimal place that our approximation is wrong. This technically is 2.9629. The actual cube root of 26 is 2.9624. So the 4th decimal place is where it goes wrong. So anyways, that's not what, this is just asking us to approximate it, but if you wanted to do what we had done in the beginning, you could still finish out with that. Another one of these ones, 14, we've got the square root of 80. So what basically perfect square is close to 80?
9 squared.
Yeah. So 81 square root of that is obviously 9. So this is my A and my F of A here, basically, by me doing it this way. Sometimes it gets written this way. I don't really remember what the reason for writing tangent is there, but I guess it's like basically like at that point. Anyways. But just if you see anybody write it this way, that's why it's written that way. But anyways. So I've got f of x is x to the 1/2. So what would the derivative of that be?
1/2 x to the negative 1/2.
Yep. And then evaluating that at the point, f prime of 81 would be 1 over 2 times the square root of 81. I'm just writing it that way instead. So that's 1 over 18. So then I'll set up my approximation like I did on the last one. So the square root of 80 is approximately equal to the linearization for 80, which is to have 9 plus 1 over 18 times 80 minus 81. And so then that makes that negative. So we've got 9 minus, oops, 1 over 18. That's approximately 8.94, and that 4 repeats. The actual square root of 80 is 8.9442. So again, to the basically the 4th decimal place is where it goes wrong as far as my approximation. So it's a pretty good way to do it if you, without really even needing a calculator other than, 1 over 18. It's not, you can do that by hand, not that you want to, but it's a pretty good way to approximate if you don't know. Both of these have just been off by 1, so it's just caused this number to be negative, but just be aware that obviously we can be off by more than that. One of them that you'll have is the cube root of 998. So obviously that's dealing with 1,000, so that one will actually be off by 2 when you plug it in, so just, make sure you actually look at it mathematically. Trying to see, I don't know why in those notes that was all that I did. Oh, I know what these are. Okay. Okay, the next one say to find dy and then to evaluate dy for the given value of x and dx. So 22, we have 2y is equal to x squared minus xy. X is equal to 2 and dx is equal to negative 0.05. So you may or may not remember back when we talked about the different ways to write, like, essentially a derivative. We had, you know, like, we could write it as y prime. I can write it as, like, f prime of x. I can write it as dy dx. But basically, when we had dy dx, we were just writing, you know, dy dx equals, and then we were just taking the derivative, and we weren't doing anything else with that. Well, with these, like, getting into, like, differentials and stuff like that, I have to have that dx in there. So technically, the way my answers are going to end up looking is dy is equal to whatever I get times dx. And that's getting multiplied by whatever this dx value is over here. So to do this one, I have kind of two ways I can do this. I can either implicitly differentiate, which is probably not your go-to method, or I can move this around and I can get y by itself and do it that way. So I'm going to do it that way just because I think it's easier. I only really implicitly differentiate if I don't have another option. So, and then I don't have the quotient, or I don't have product rule. I may still end up with a quotient rule by the time it's all said and done. But anyways, so I'm going to add xy over. So 2y plus xy equals x squared. Take out a y. 2 plus x equals x squared. And then divide. So unfortunately, I am going to have a quotient rule, but that's fine. So y equals x squared over 2 plus x. So then I can take the derivative of this. So I'm going to write this as dy equals, and then when I'm done, I'm just going to write dx at the end. So we have the derivative of the top, 2x, times the bottom, 2 plus x, minus the top, x squared, times the derivative of the bottom is just 1. And then all over the bottom squared, so that's 2 plus x squared times dx. So this is the initial derivative where it says find dy. This is the first part. Now they want me to evaluate it for the given values of x and dx. So I don't even need to, like, I mean, if you wanted to go ahead and simplify this farther when you find your dy, you can. If they ask you to do this as a multiple choice question, they probably are going to have multiplied it through already and simplified it down. But since I know I'm ultimately plugging in numbers, I don't really need to simplify it because it's going to simplify itself down nicely by the time I'm done. So dy equals 2 times 2 times 2 plus 2. Minus 2 squared, that's a lot of 2's, over 2 plus 2 squared times negative 0.05. So basically on top I've got 4 times 4 is 16 minus 4 over 16 times the negative 0.05. At this point, I'd probably just grab my calculator and throw this in there because I've got 12 over 16 times negative 0.05, and I get negative 0.0375, and that's where that decimal stops. And so that's your evaluation of what dy is equal to with the given x and dx. So these will be kind of a good, like, finding derivatives refresher on those ones. Once you do that, then you're just plugging in numbers there to solve it. So, I'm going to do, like, 2 more problems, not of this type, but of a different type, and then save the last few things for tomorrow. That are, like, finding the change of, like, in the volume of, like, shapes and things like that. Anyways. So the last ones are to find the differential. So when it tells you to do that, they're going to give you d of e to the 5x plus x to the 5th. All they are telling you to do is take the derivative of that. This is just a different notation to do that. And they want you to write dx at the end as part of the differential. So this is the derivative of this whole thing. So derivative of e to the 5x would be e to the 5x times 5. And then plus 5x to the 4th. And then that whole thing, so I usually put parentheses around that, times dx. It doesn't really matter if you leave the 5 behind the e or if you put it in front. A lot of times it just looks nicer if we do like 5e to the 5x, but again, up to you. Plus 5x to the 4th dx. You could go as far as to take a 5 out, but you still have to have it all in the parentheses, so it's really not going to make a difference if you like take this 5 out of here, because it's still going to basically be like inside the whole differential. But that's your answer on one of those. And we'll look at 26 just because it's a good refresher on derivatives of exponentials. So we've got d of 8 to the x plus x to the 8. Do you happen to remember what the derivative of something like 8 to the x is? I feel like this is one of the ones I have the hardest time remembering.
I don't remember.
It is, we copy it down exactly, and then it's times the ln of whatever the base is. So it's 8 to the x times the ln of 8 is the derivative of that one. And then this would be plus 8x to the 7th. And then dx. And that's all you have to do on these ones. So those ones are relatively easy, but we'll pause there because there's not enough time to get into the other ones. And then I'll just give you problems for everything after that tomorrow, and I'll make sure that we've covered everything because I kind of have like multiple sets of notes here, so I'm trying to make sure that I've gotten everything that's like important. So